Hello everyone! In the last class, we started from two types of rate of change problems and abstracted the concept of derivatives based on their commonalities. Can you write the formula for calculating the derivative of the function y equal to fx at x equal to x0 and explain the meaning of the derivative? The function y is equal to fx, and the derivative at x equals x0 is equal to. When delta x approaches 0 infinitely, the average rate of change delta y is greater than the limit of delta x. When calculating, we can first find the expression for the average rate of change delta y compared to delta x, and then take its limit. Derivative is the mathematical expression of instantaneous rate of change. It represents the instantaneous rate of change of function y equal to fx at x equal to x0, reflects the variation of the function y equal to fx near x equal to x0. Everyone knows that numbers and graphics are two complementary objects in mathematical research. Does the derivative have its geometric significance? We know that the derivative is the limit of the average rate of change. Everyone can first think about the geometric meaning of the average rate of change. The ratio of the average rate of change delta y to delta x is equal to the ratio of the change in the function value to the change in the independent variable. We can also write the denominator as the difference between two independent variables. What can you think of from the structure of the equation? Have you all thought of the slope of a straight line? This equation represents the slope of the line passing through point P0 and point P, where the coordinates of point P0 are x0 and fx0. The coordinates of point P are x0 plus delta x, fx0 plus delta x. These 2 points are clearly on the graph where the function y is equal to fx. Let's make a schematic diagram. The horizontal axis of point P0 is x0, and the vertical axis is fx0. The horizontal axis of point P is x0 plus delta x, and the vertical axis is fx0 plus delta x. Since delta x can be positive or negative, but not 0, point P may be to the right or left of point P0. Let's first draw the situation where point P is on the right side of point P0. From the figure, we can see that the line passing through point P0 and point P is a tangent line of the fx image with function y. Therefore, the geometric meaning of the average rate of change is the slope of the secant P0p. The derivative is the limit of the average rate of change, and we already know the geometric meaning of the average rate of change. So how should we understand the geometric meaning of the derivative? When delta x changes, the position of point P also changes accordingly. Thus, the position and slope of the cutting line P0p also change accordingly. When delta x infinitely approaches 0, point P along curve y is equal to fx infinitely approaching point P0. Since delta x can be positive or negative, we will explore it separately. Let's first look at the case where delta x is greater than 0, where point P is to the right of point P0. As delta x continues to approach 0, point P along curve y equals fx and continues to approach point P0. When delta x approaches 0 infinitely, point P approaches point P0 infinitely. The tangent line P0t infinitely approaches a certain position, and the slope of the secant infinitely approaches the slope of the straight line at this determined position. When delta x is less than 0, k is on the left side of point P0 when delta x approaches 0 infinitely, approaching point P0 infinitely along the curve. The cutting line P0p infinitely approaches the same determined position as just now. The slope of the secant P0p is also infinitely close to the slope of the line that determines the position. So what is the line that determines the position? It is the tangent of curve y equal to fx at point P0. Okay, can you define the tangent according to the process just now? We can define this as taking any point P on the curve y equals fx, and the coordinates are x, fx. If point P is infinitely close to point P0, x0, fx0 along the curve y equal to fx, the secant P0, P infinitely approaches a certain position. The straight line P0, t that determines the position is called curve y equals fx, and then point the tangent at P0. We also learned the definition of tangent in junior high school. Do you remember how to define tangent in junior high school? In fact, in junior high school, we only defined the tangent of a circle. If a line and a circle have only one common point, then we say that this line is tangent to a circle. This line is called the tangent of a circle, and this point is called the tangent point. Are our two ways of defining term consistent? We examine this issue from two aspects. The tangent of a circle is defined from the number of common points of a line and a circle. Is this definition applicable to any curve? You can try to give a counterexample. Curve y is equal to x squared. The straight line x equals 1 and the parabola has only one common point. The line x equals 1 is obviously not the tangent of a parabola. For another example, if the curve y is equal to the third power of x, we can make its tangent at points -1 and -1, and the number of intersections between this tangent and the curve is obviously more than 1. It can be seen that our definition of the tangent of a circle in junior high school is not suitable to be extended to any curve. So is the definition of tangent given today by approximation applicable to the tangent of a circle? As shown in the figure, the straight line P0P is a secant of the circle. When point P is infinitely close to point P0 on a circle, the secant P0P is infinitely close to a certain position. Only one of the number of common points between the line and the circle that determine the position conforms to our definition of the tangent of the circle in junior high school. It can be seen that today we define tangents in a more general way. Back to our previous question, now can you tell us what the geometric meaning of derivative is? From our previous analysis, we can see that the function y is equal to fx. The average rate of change from x0 to x0 plus delta x, delta y, is greater than delta x. Its geometric meaning is the slope k of secant P0P. On the one hand, according to the definition of derivative, when delta x is infinitely close to 0, the limit of the average rate of change is the derivative value of function y equal to fx at x equal to x0. On the other hand, according to the definition of tangent, when delta x infinitely approaches 0, point P infinitely approaches point P0 along the curve. If secant P0P, if it can infinitely approach a certain position, that is, the tangent P0t, then the slope k of the secant will infinitely approach the slope k0 of the tangent P0t. This means that the function y is equal to the derivative of fx at x equals to x0, and its geometric meaning is the slope of tangent P0t with k0. In this way, the derivative of the function y equals fx at x equals x0 establishes a corresponding relationship with the slope of the tangent at point P0, coordinate x0, and fx0 of the curve y equals fx. Attention please! The correspondence between function and curve. Find the corresponding relationship between the point of derivative and tangent point. With this correspondence, in the future, when we study the derivative of a function at a certain point, it can be transformed into the slope of the tangent of the corresponding curve at the corresponding point. To study the tangent of a curve at a certain point, we can calculate its slope by calculating the derivative of the corresponding function at the tangent point. We have completed the conversion between numbers and graphics. Next, let's take an example to find the tangent equation at point 1 and -1 where the curve y is equal to -2x squared plus 1. We know that the tangent point is a point on the tangent line. We only need to calculate the slope of the tangent line, and the equation of the tangent line can be determined. According to the geometric meaning of the derivative, the slope of the tangent is equal to the derivative value of the corresponding function at the tangent point. Let fx be equal to -2x squared plus 1, according to the geometric meaning of the derivative. The tangent slope k of the function image at point 1 and -1 is equal to the derivative value of the function fx at x equals to 1, according to the calculation formula of the derivative. We substitute the analytical expression of fx into the collation, and we can get that k is equal to the limit of -2 delta x minus 4 when delta x is infinitely close to 0. When delta x is infinitely close to 0, the delta x of -2 times is also infinitely close to 0, and then subtracting 4 is infinitely close to -4, so k is equal to -4. We then take the coordinates 1, -1 and negative slope 4 of the tangent point into the point skew equation, and we can get that y minus -1 is equal to -4 times x minus 1. After sorting, 4x plus y minus 3 equals 0. This is the equation of the tangent we are looking for. The key to solve the tangent problem is to use the geometric meaning of the derivative to calculate the slope of the tangent. Let's take a look at this graph when defining tangent. There are many lines in this graph. Which line is closest to the curve near the point P0? It is not difficult to see from the picture. The tangent of the curve passing through point P0 is closer to the curve near point P0 than any secant. Therefore, near the point P0, the curve y is equal to fx, which can be replaced by the tangent P0p at the point P0, which is an important method of thinking in calculus. Next, we return to the initial problem of high diving. The figure is an image of the height of the athlete's center of gravity relative to the water surface in high platform diving. The function ht over time is equal to negative 4.9t squared plus 4.8t plus 11. Please describe the change of the comparison curve ht near t equals t0, t1, and t2 according to the image. How to describe the change of curve ht near t equals t0, t1, t2. From what we have just learned, you know that you can use tangent to approximately replace the curve near the tangent point, and use the slope of tangent to describe the change of curve near the tangent point. We make the tangent lines of the curve ht at t equals t0, t1, t2 respectively. When t equals t0, the tangent LO of the curve ht at t equals to t0 is parallel to the t-axis, and the slope is 0, that is, the derivative of the function ht at t equals to t0 is equal to 0. This means that near t equals t0, the curve is relatively flat and there is almost no rise or fall. When t equals t1, the slope of tangent L1, that is, the derivative of function ht at t equals t1, is less than 0. This means that the curve is descending near t equals t1. That is to say, the function ht is monotonically decreasing near t equals to t1. When t is equal to t2, the slope of tangent L2, that is, the derivative of function ht at t is equal to t2, is less than 0, which means that the curve is falling near t is equal to t2. That is to say, the function ht is monotonically decreasing near t equals t2. Through the analysis, we found that the curve HP decreased near t equals to t1 and t2. Is there any difference between the downward trend at those two moments? It is not difficult to find that the inclination of straight line L1 is less than that of straight line L2, which indicates that the curve HD decreases slowly near t equals to t1 than near t equals to t2. In this problem, we used the tangent approximation to replace the curve near the tangent point and used the slope of the tangent to describe the change of the curve near the tangent point. The positive or negative slope reflects the increase or decrease of the function, and the size of the slope reflects the speed of the increase or decrease. We can see from the process of finding that the function y equals fx and the derivative at x equals x0. The derivative of function fx where x equals x0 is a certain number, so that when x changes, it is a function of x. We call it the derivative of y equals fx, or derivative for short. In this way, y is equal to the derivative of fx, which is equal to the limit of the ratio of fx plus delta x minus fx to delta x when delta x infinitely approaches 0. In this lesson, we have a more general definition of tangent through the idea of limit, and through exploration, it is found that the geometric meaning of the derivative is the slope of the tangent of the curve y equals fx at x equals x0. By observing the curve and its tangent, we find that the tangent can be used to approximate the curve near the tangent point, and the slope of the tangent can be used to describe the change of the curve near the tangent point. This is an important way of thinking in calculus. That's all for today's class. Goodbye.